Hello, everybody. Today we're going to be going over limits in calculus. So, a limit essentially is going to be, you're going to use this notation, the limit as x approaches. Here, I'll draw that a little bit better. A of f of x is equal to L. So, let's draw a graph to show exactly what this is trying to solve. Let's say we have the limit as x approaches just some number, 1, of x plus 3. So, what we're saying is that we have a graph like this, and let's plot x plus 3. So, 3 is probably right here, and their slope is 1. Just go up 1, right 1, and then we can just draw our line right there. So, essentially, I'm going to use other colors. Let's say this right here is x equals, hold on, actually it's probably best to actually write it a little more accurately here. So let's say this is about x is about 1, so this is x equals 1. What it's saying is it wants to know what y value that it's going to be approaching as this line is going from here. And this means for both sides too. So it's as it's approaching from here and also as it's approaching from there. But in this case, it's a linear function and it's a normal function, so they will be the same. In this case, all you have to do is do some direct substitution. All you have to do is just plug in 1 for x plus 3. So in this case, we know that 1 plus 3 equals 4. So that means that this limit is 4. So that means this is y equals 4 right here. So essentially, from both sides, it's as x approaches 1, this function is going to reach 4. Now, let's consider some other things. So, let's say we have another one. Probably best to use a less bright color here. Limit as x approaches, let's say 2 of x minus 6 over x plus 1. Alright, something else you need to consider is asymptotes. If you use direct substitution and you plug in something and you get 0 over 0 or some quantity over 0, you're going to need to use a different limit method. In this case, we don't have any, so we can just use some direct substitution. So this is going to be 2 minus 6 over 2 plus 1. And 2 minus 6 is negative 4, and 2 plus 1 is 3. And we can't simplify any further, so that's going to be the limit for that function there. Now, let's move on to a different case. Let's say we have the limit as x approaches 2 of x minus 2 over x squared minus x minus 2. Well, the problem is that if you use direct substitution here, you're going to get 0 over 0. And this is no good. You do not want this. You definitely do not want that. So, in this case, when you're working with this, there's two things you could do. I will explain the other one later in the video because it deals with derivatives. But for now, what you can do is you can see if you can factor it. So in this case, we have this, which is a negative 2. So here, I'll highlight this, negative 2. And then we have a negative 1. So if we want to factor this, we want to know what two numbers multiply to negative 2 and then add to negative 1. In this case, we can just use the numbers 2 and 1 because 2 and 1, but now which one do we make negative necessarily? So we want to make at least one of them negative because this c coefficient, this y-intercept is negative. So if we want to make a negative result, -1, we're going to have to make the bigger number negative. So now we know that this expression is equal to, let's rewrite our limit. Make sure to always be rewriting your limit until you solve it, of x minus 2 over x minus 2 times x plus 1. Now, as you can see here, we can cancel out some factors here. These two. And now we're just left with the limit as x approaches 2 of 1 over x plus 1. So now all we got to do is just directly plug that in. Now 1 over 2 plus 1, which is equal to 1 over 3. So in this case, that is going to be the limit for that one. So make sure that you could actually factor out your equation to see if you can evaluate the limit with direct substitution. Let's try another example. Let's say we have the limit as x approaches 2 of 3 over x minus 2. So, I'm going to introduce a new concept called left and right-sided limits. So, as you know, this function, what's going to happen is it's going to have an asymptote at x equals 2 because that's what makes the denominator 0. So, what's going to happen is that we're going to take it from the left side, which means that we're going to have a number that is just a tiny bit smaller, infinitely smaller, or like an infinitely small amount smaller than 2, and then an infinitely less amount larger than 2 on the right side. So, as you can see here, our direct substitution won't work because we get 3 over 0, and there's no factoring we can do, so we need to resort to left and not right-sided limits. I will refer to the right-sided limits as blue. So, let's say we have the limit as x approaches 2, and we're going to use this notation. When it's positive, we use a plus sign of 3 over x minus 2. So as it approaches it from the right side, we're just going to pick a number that's barely smaller than 2, or barely bigger, sorry, than 2. So in this case, let's just choose 3 over 2.00001 minus 2. So let's just evaluate. 3 over 0.00000, and then we're obviously going to put repeating and then put a 1 on the end. So when we have a number on top divided by a super small quantity, this is going to reduce to a bigger number. In this case, this number is infinitely close to 0. So in this case, this is going to approach infinity. So let me rewrite this. So we know that the limit as x approaches 2 from the right side is infinity. Now let's check from the left side. So the limit as x approaches 2 from the left side, we're going to do a number that's barely smaller than 2. So we're going to take 3 over, let's say, 1.9999 minus 2. So this is going to be 3 over negative 0.0000, and then there's going to be a 1 on the end. So what's going to happen is that we have the same situation, except it's negative this time. So in a fraction, a positive over negative is going to be a negative. So in this case, we're going to be approaching negative infinity from the left side. Now that we've taken both sides of this limit, we can say something about all of this. So that means that if the limit as x approaches a from the right side of f of x is equal to the limit as x approaches a from the left side of f of x, then we know that the limit of x approaches a of f of x exists. So in this case, infinity and negative infinity aren't the same thing. So this limit has a property called does not exist. So all you say when you encounter this is that does not exist, DNE. And that's your answer there. The limit does not exist. Let's move on to the next one. Now, let's start using infinity more in our limits. Let's say we have this one. Limit as x approaches infinity of 1 over x, and then let's evaluate it. So one thing you can do is you can use your logic and reasoning. So you could say that 1 over some quantity a, see, if a is bigger than 1, that means, well, let's call this b. That means b is going to be larger than 1 over a in this case. Well, actually, hold on. Probably not the greatest idea to write it like that. So that means b is essentially going to be bigger than 1. But if a is less than 1, that means b is also going to be less than 1. So, wait, hold on. Oh, wait. That's why. So the product is going to actually be, is actually going to be bigger. So think about it. 1 over 0.00001. This is just going to be 1 over, and then 1 over, well, there's 3 zeros, so 1 over 100. Well, actually 1,000. So 1 over 1,000 simplifies to 1,000. Well, in this case, it's actually 10,000. So this is going to be 10,000. So as you can see, the smaller the number is in the denominator, the bigger the actual number is. So we're going to use that reasoning that as x approaches an infinitely large number, we know that this number 1 over x, if we plug in some super big number, it's going to produce, so 1 over x equals b. That means b is going to be way smaller than 1. So that means that this is actually going to be 0. Because as x is approaching infinity, we're not going to be tackling with negative numbers. We're just saying that 1 over an infinite amount of parts is equal to 0, which is going to be the property of all limits like this. So when you see 1 over some quantity, and then we have the limit as x approaches infinity of it, if infinity is in the denominator, it's going to be 0. But we can also just take left and right side limits. So limit as x approaches, let's say, infinity. Well, we're going to have to do it from the left side. It's going to equal 1 over x. So this is just going to be, well, we don't really have anywhere to go from the right because infinity is itself a right quantity. So in this case, it only has the left side limit because the right side limit is not defined. So that means the left side limit is going to equal the actual limit. So in this case, the limit as x approaches infinity of 1 over x is equal to 0. Now, let's solve another one like this. Let's say the limit as x approaches negative infinity of the square root of negative x. So for this one, what it's going to say is that this limit here is essentially approaching negative infinity. So as this number is closer, like let's say we plug in a number like negative like 100 in here. This number, square root of 100, is going to equal 10. Now let's plug in even, an even more massive number. Let's say we have, I don't know, like 10,000 under the square root. Or we at least say we have negative 10,000, and negative 10,000 is equal to just the square root of 10,000, which is just 100. So we're just going to keep going up and up and up and up. And since the square root function is actually an increasing function, we're going to say that this is actually going to approach infinity. So that's how you use your basic logic and reasoning to solve limits as they approach infinity. Because obviously you cannot directly substitute infinity as it is a mere concept. Now, let's go over something else. Let's say the limit as x approaches infinity of 6x squared minus x plus 3 over 7x plus 1. Okay, so what's going to happen here is that we're not gonna want to compute this because we have infinity, and then we're gonna have infinity squared, and then minus infinity, and it's going to get indeterminate, and we will not be able to solve it. But we're gonna use a property that essentially is going to outline the highest increasing or decreasing part of our functions. So what you want to do here is you want to find which fraction, part of the fraction, that has the highest degree polynomial, and then you just want to get rid of the others because they're not going to grow as fast. So for example, if we have x squared and we have x to the fourth, as you can see, as x approaches infinity, let's say we have like 10 to the fourth, and then we have 10 squared, one's going to be 100, the other one's going to be 10,000. So we know that x to the fourth is going to grow faster. In this case, let's outline what's going to grow faster on each one. So in this case, here on the top numerator, our x squared with our 6 coefficient is going to grow the fastest. So we can just omit this, and then on the bottom, our plus 1 is not going to grow fast at all. So we're just going to just omit that, and now we're just going to try to find the limit as x approaches infinity of 6x squared over x, or over 7x. So essentially what's going to happen is we're going to have just 6 over 7 times x. And as x approaches infinity, we're just going to have 6 over 7 times infinity, which is just going to be infinity. So in this case, this limit is equal to infinity. Because the degree on the top is larger than the degree on the bottom. Now, let's go over one more of those specifically. Let's say the limit as x approaches infinity of 6x plus 2x squared minus x to the fourth over x to the fifth minus 1. So what's going to happen is we're going to have a limit as x approaches some value, and we're just going to use this principle again. So our highest degree on the top is this one. So let's omit these others. And then our highest degree on the bottom, we're just obviously going to omit the 1, and then we're just going to keep with x to the 5. So now we have negative x to the 4th over x to the 5th. And this is just going to reduce to negative 1 over x. Now, essentially, we already went over that the limit as x approaches infinity of 1 over x is just 0, and negative 0 is just 0. So now we're just left with 0. So that's going to be our limit there. So if the degree on the bottom is taller, or not as taller, is bigger, if there's a higher degree on the bottom, the denominator, that means that the function will likely be approaching infinity. So let's move on to something called L'Hopital's rule. This guy, specifically, he made this rule that says that the limit as x approaches a of f of x over, let's say, g of x, doesn't necessarily have to be in this form, but this is the most common form, is essentially equal to the limit as x approaches a of f prime of x over g prime of x. So what's going to happen is that we're going to have a situation like earlier where we have 0 over 0, and then what happens is that we then can't factor it, so then we're going to have to use L'Hopital's rule. So let's use this limit for practice. Let's say the limit as x approaches 1 of x to the 3rd minus 1 over natural log of x. So for this one, we're essentially going to take the derivative of both sides. So let's just keep the 1 here. So now we're just going to take x to the 3rd minus 1 over ln x. And then we're just going to take the derivative on both sides. Now we just use our power rule and our basic derivatives. So this is going to be 3x squared on the top, and this is going to equal, well, the derivative of natural log of x is just 1 over x. And then we know that when we divide by a fraction, we're just multiplying. So realistically, we're just multiplying by x here. And this is just going to be 3x to the 3rd. So now we know we have a limit as x approaches 1 of 3x to the 3rd. Now we can just easily substitute in. We can easily substitute in 1 here. So now all we got to do is then say that we have 3 times 1 to the 3rd, and then this is going to equal 3. So that is going to be the limit as x approaches 1 of x to the 3rd minus 1 over the natural log of x. As you can see, if we did direct substitution, where we would have 0 over 0, which is obviously undefined. Let's do one last problem. It's not specifically based on L'Hopital's rule, but I would like to see how you guys at home would actually solve this one specifically. I'll give you a moment to try to solve this one. So, what's going to happen is we're going to need to use our right and left side limits, because if we plug it in, we're going to have negative 4 over 0, and that's not going to work. And we don't have 0 over 0, so we can't use L'Hopital's rule. So what's going to happen is, well, the thing is with this function specifically, let's actually make it a little bit easier to understand. So this is going to be equal to the limit as x approaches negative 4 of x times 1 over square root of x plus 4. So what's going to happen is that we're going to have to take the right left-handed side limits. But in this case specifically, we have a square root function on the bottom, And we know that the domain, or that our square root inside, has to be greater than 0. Because if it's less than 0, then we're going to have imaginary or complex numbers, and we cannot work with those in limits necessarily. So let's take what we have, and let's just take the left-sided limit. Approaches. Well, actually, if we think about it, if we're taking a limit from the left side, we're going to be a number slightly smaller than 4, so negative 4.00001. And if we add 4 to that, there's still going to be a negative number, so we can't take it from the negative side because it's going to be undefined. So we actually need to take it from the positive side, in this case, the right side. And then now we just got to do x times 1 over the square root of x plus 4. So now all we got to do is plug in a number that's slightly bigger. So let's say we have negative 3.99, and then let's just put it over negative 3.99 plus 4. This is just going to be negative 3.99. Obviously, just keep it normal. And then we're just going to keep the square root. Well, this is just going to be some number 0.00. Well, in this case, we just put 0.1. And from here, we know that if this number is getting infinitely smaller, we're essentially saying that this is going to be approaching 0 here, in here, but we have a negative number here. So if this is approaching 0, that means that this is actually going to go to negative infinity, because we have a negative in the numerator, and we have a positive number always in the denominator. In this case, as this number is going to decrease, this is going to be something like 0.00, and then we're just going to have all these zeros repeating, and then we're going to have a 1, and we're going to take the square root, and then as these numbers get closer and closer, what's going to happen is that then it's going to approach negative infinity. So that is going to be the answer for that one specifically. Now, it is good to mention that I did technically forget to multiply by negative 3.99, but in this case it's not very significant because we're dividing by an infinitely small number anyway, so our numerator is actually increasing at a slower rate. In fact, it's a finite answer, so it actually will not be increasing. Anyways, I hope you like this video, and I will try to get back to my daily upload schedule at some point. You never know. But anyways, goodbye.